Hi everyone, welcome back. Now in this part 2, we'll be assigning the area of reinforcement required for both tension and compression reinforcement. And just before going to this part, let's just recap what we had in part 1. So we were giving as simple as about a beam. It has an effective span of 6 meters. And also the grade of steel and the grade of steel and the grade of concrete were given. Of course, the loads on the beam must be given as well, so that you can determine the ultimate moment on the beam and for the bending design, and the maximum shear force for the shear links design. Now, we said that the simplest water beams can also be seen in RC structures. But the thing is, when we talk about rectangular sections, they might not appear as often when compared to L and T beams. And this is due to the fact that we always have the monolithic pouring of concrete. So the next step was to define our tri-section. And to do so, well, we had to refer to a table given by the Eurocode 2. Now there is the L over D, the effective span to the effective depth ratio, and we said for the highly stressed concrete, that means we're talking about beams. Now our system here, it is as simple as about a beam, and this table is valid for flexural members, that is slabs or beams, and that we took this ratio, so L over D, we took it as 14. From there, I can simply find the D, right? And once I find the D, I can just round it up and then find the B as well. And that, I think we paused the video up to this point where we defined our section. And we said for our section, it must be doubly reinforced. Right, let's now just move on and determine the area of reinforcement. Now, to understand how we derive this, well, I'm not going to discuss it here in this video, but I made another video for the doubly reinforced section analysis. You can just check it there in my channel. Anyways, so all what I need here is the K. I already determined the K. The K balance is just the 0.167. I have the grade of concrete, BD, everything that I need is in this equation. So I just substitute, and this is what I get. Now you have to pay attention for this. Here we are talking about what? The area of compression reinforcement required. This is the required, not the provided. We will need this later on when we check the deflection. Anyways, I'm a bit skeptical about this. See, the number here is very, very small. It's just 81 millimeter square. And when compared to this area of tension reinforcement, this looks reasonable. Just before going to further steps, we need to check the minimum area of reinforcement. Now, why do we need to check it with a minimum area of reinforcement? Is something to do with the durability, with the controlling of cracks, something that we need to do in detailing. This is the limit. So this is the minimum area of compression reinforcement that we must provide. And it's given by the code as 0.2% of the gross area. And for the minimum area of tension reinforcement, it's 0.26 FCTM. So the FCTM is what? Is nothing but the mean tensile strength of concrete. So I guess we have everything that we need here, and we're gonna check first the compression reinforcement. So 0.2% of the gross area. Just plug and check, you'll see that we have 300 here. So this is the minimum. I cannot go beyond this. My area here is just H1. So I'm going to change this. Right. That means I'm going to take something like 300 or more. Now let's just check this. First of all, we find the mean tensile strength of this grade of concrete. And it happens to be 2.9. So 10%, almost like if you just take the 10% here, it is 3. So this is 2.9. It is more conservative. And then we just find the minimum area of tension reinforcement set by the code. So 0.26 times the tensile strength divided by the grade of concrete, 500 yield strength, times BD. But first we have to compare it with this. And since this one is larger than this one, so I'm gonna go ahead and select this one. Right, so 0.15% B times D. Now this time we are not taking the gross area. This is just B times D. And it comes out to be 202.5 millimeters square. And this is way less than what we are required to provide. Right, now we just, we have to select, I'm pretty sure that you are very familiar with this table. So this gives the bar size, okay? And this is against the number of bars. Now I'm gonna select something closer to this. This is for the tension, this is for the compression reinforcement. Probably this one. So I'm gonna provide 3 bars in the compression zone. Each has 12 diameter. And for the tension zone, I'm gonna provide 7 bars. Each has a diameter of 20. So that's it. The only thing here, since I checked it with the minimum area of reinforcement set by the code, I also have to check it with the maximum area allowed for the reinforcement, and it's given as 4% of the gross area. So it has to be less than or equal to 4% of the gross area. This plugin check, you'll see it is 6,000 millimeters square. None of these is even close to this number. So I am fine with the maximum area set by the code. So I'm providing 3H12 for compression zone and 7H20 for the tension zone. So that's it for the rebar. That's the area of the reinforcement. Now we carry on, and we'll have to do something here. Just bear in mind that we have the B, and the B is just 300. Now for the compression reinforcement, I guess it's fine. I mean the spacing, I can just put them in just one line, and that's totally fine. I mean I have plenty of space here. But when it comes to the tension zone, is it possible that I put 7 rebars in just one row? Let's just calculate this. Now the minimum distance, the minimum clear distance between one bar to another has to be, and this is set by the code, has to be 20 millimeter, or the aggregate size plus 5, or the bar diameter. Here we have the bar diameter as 20. Since we are not giving the aggregate size, so I'm gonna go ahead and just take the bar size, which is 20. So I'm gonna keep a distance of 20. This is the clear distance between one bar to another, so 20 millimeter. And that, let's just make this quick calculation. Right, so we said the clear distance must be 20, and this is set by the code. Now we have 300, that's the B, minus, okay, we have 7 bars, right? The number is 7 in just one row, and we have, each has 20 millimeter diameter. This is plus the spacing between them. So we have 1, 2, 3, 4, 5, 6. And the spacing we said has to be 20 millimeter. That's the minimum. Plus we have the links as well. So this is 2 times 8. We assumed the links to be 8 millimeter. So we're gonna end up having this number 24 millimeter. That means I'm leaving a space of 20. That means I'm leaving a space of what? 12 millimeter here, and another 12 millimeter here. I don't even have to go back and check this by the code. 12 millimeter is way too small, and that, I'm gonna change my arrangement. So instead of putting one layer of reinforcement, I'm gonna go ahead and put 2 layers of reinforcement. So I'm gonna rearrange this. So I'm gonna put 5 rebars at the very bottom, the first layer, and for the second layer, I'm gonna put just 2 rebars. I'm not changing the number of rebars. I'm only just rearrange my rebars such that they can occupy the space without causing any troubles later on. So if I just if I just calculate this again, now instead of having 7 bars at the very bottom, okay, now we only have 5. So 5 times 20 plus, now the spacing also 1, 2, 3, and 4. So 4 times 20 plus 2 times 8, the links. So that gives me 104. Now 104 divided by 2 for both sides gives me what? 52. So I'm gonna keep a distance of 52 from the extreme fiber to the face of the links. Okay, 52 millimeter on this side and another 52 millimeter on this side. So what you can tell here is that 52 is bigger than 12, and of course this is more conservative for me, and well, I'm gonna put it in this arrangement. Now I can tell that we have successfully assigned the area of reinforcement required for our cross section, and probably by doing so I think we are done with the bending design. This is the rebars that we need to encounter the applied bending moment. Just remember, yet we haven't designed the shear links, and hopefully we're gonna talk more about this in the next part. Now, just before moving to the next part, there's something important that we have to do here. It is the deflection check. And well, why do we have to put the deflection check right now? Why couldn't we just do it in the very beginning of this video? The answer is that because, well, we have determined the area of reinforcement, okay? And since we have the area of reinforcement for both compression and tension, and I guess we have everything that we need to determine or to check the deflection using the effective span to the effective depth ratio, then why would we just delay it until the very, very end of our designing process? And then we might be surprised that the deflection doesn't meet the requirements with the code requirements. Okay, now for better understanding of deflection, I'm gonna just open up the slide, and we'll have to go through one example here that would hopefully make it clear for you, understanding the effective span to effective depth ratio and how to implement this in your designing process. Now the code, well, you can actually calculate the deflection in millimeter. Okay, that is, you determine the deflection, the final deflection, that's the long-term deflection. And well, if you do so, well, the process is a bit lengthy and it gets really tedious because you'll have to, I mean, it's not that difficult, but it takes time. And well, we have to go through the uncracked section, we'll have to go through the cracked section, we'll have to consider shrinkage and the creep. And then once you get the final deflection, the long-term deflection in millimeter, you'll have to compare it with the, it's either you compare it with a span over 250, okay, or if you want to avoid any damages to your finishes or fittings, you just compare it with the span over 500. And that's up to the client. And the client can really tell you, I mean, if they want you to calculate the deflection in millimeter, then they just gonna ask you to do so. And it's going to be lengthy. It's either you calculate the deflection or only you check the span to effective depth ratio. Now, what is the span to effective depth ratio? You'll need two equations. So this is the L over D. This is what we are aiming to find. All of this depends on the row value. So the row, we know that it's the percentage of tension reinforcement, the required one, not the provided one. Okay, and we have the row O here. That's the reference reinforcement ratio. And for the same grade of concrete, it is going to be a constant. Okay, all right. So if my row is less than or equal to the row reference, then I'm going to use this one. But if it's the opposite, then I'm going to use this one. That's it. That's the whole story of this. The K, we talked about the K. It is within that table. It is given by that table I showed you very early. I got everything that I need here. The rho prime is the percentage of compression reinforcement required. So probably have everything that I need to check my span to effective depth ratio. Alright, as I said, so the K again, it is from this table, and well, it depends what kind of structural system that you are using. For a simply supported beam, it is just 1. When you talk about in-span continuous beam or slab, it is just 1.3. Everything that you need is just within this table. And just to make sure, now we are talking about the allowable L over D. This one will be compared not to the span over 250 as I mentioned earlier. This one will be checked with the actual span to depth ratio of our beam. Well, this is not yet the allowable span to depth ratio. There is what's so called the modifications. So let me just put it in this way. If you just determine the L over D, right, and that you know what you are providing here, okay, what you are putting here, the rho, is for the required area of reinforcement, but this is not the one you are providing. Okay, so you're providing something more than that, more than the required. And that, well, I mean, it is very reasonable that if you're providing more than the required, then the deflection gonna get reduced. And this is the first modification here. I have the 500, this is a constant. I have the grade of concrete, I have the grade of steel. It might be 500 less or more, just put it there. The area of tension reinforcement provided divided by the required. This should be less than or equal to 1.5. Once I determine this, okay, first of all, I just find the L over D and then multiply it by the modifications. This is the first modification. Once I determine this, I just multiply it by the L over D. So this is basically the first modification. And the second modification here will get my deflection increased. Because see, if I'm talking about spans larger than 7 meters, okay, what happens to the deflection? It will increase, definitely. And the code puts this span 7 meters. You will have to modify your L over D by multiplying the 7 divided by your span. Say your span is more than 7. Say your span is 8 or 9 or even 10. So 7 divided by 8 times the L over D, the one you find it here. This is true for the beams and solid slabs. That's the modification that we have to apply when we talk about flat slabs. Right. Now, I'm pretty sure that most of the students are very familiar with this graph. Now, I can just simply, okay, check my ratio from here. I don't have to go through that equation. I can just select my ratio from here, and that depends on the area of tension reinforcement required over the BD. Okay, this is just the rho, and say that my rho is 1.2 and I'm using the grade 30. So 1.2 up to here, it gives you a ratio L over D of approximately 15. That's my L over D. But just bear in mind, you are talking about a simply supported beam. The K is 1 here, and it has no compression reinforcement. Okay, this works perfectly for slabs, but for beams, well, sometimes we don't really have single reinforced sections. We cannot really refer to this graph. We'll be using the equation instead. Anyways, if my K is not 1, I'm gonna apply the same modifications that I talked about, except that I'm gonna add one more thing here. It's the K. So if my K here is not 1, that's fine, that's totally fine. Say my K is 1.3, then I'm gonna modify my L over D. I'm gonna apply all the modifications, and then there's this modification. My K isn't 1, so I'm just multiply 15 times 1.3. So if my K isn't 1, that's fine, I can refer to this graph. But just remember, you shouldn't really have any compression reinforcement if you wish to use this graph. Right, Just before going back to our design problem, I'm gonna have this quick example. So we are asked to check the deflection for this beam, and we have everything that we need. We have the area of tension reinforcement provided, okay, we have the D, we have the B, and also we have the area of reinforcement required. Okay, so let's just do it. Now, as said, we have two equations that depends on the row reference and the row of tension reinforcement. So it is either I use this one or this one. So this is my row for the tension reinforcement required, and as I said, it's given in the example, so it's 1100 divided by BD gives me this answer, and I'll have to compare it with the reference reinforcement ratio that depends on the grade of concrete, and that gives me this answer. So this one is clearly bigger than this, so I'm using the second equation, right? The K, just if you refer to that table, you'll find the K to be 1.3. This is a continuous beam, and this particular one is an end span continuous beam, so my K is 1.3. Clearly I don't have any compression reinforcement, so my rho prime is 0. I've got everything that I need to put in this equation, so just plug and check. You'll find your allowable L over D to be 24.5. Yet this is not my final L over D. I'll have to modify it. So to do so, first of all, the area of reinforcement provided is larger than the required. You can tell that very clearly. So my grade of steel is 500, so just the same. This is 1, but the provided divided by required gives you 1.145, and that, well, take this answer, multiply it by your L over D. That, as I said, since you are providing more area of reinforcement, this will increase your allowable L over D. But yet this is not the only modification. Now my span is larger than 7, so I have to apply another modification, and simply this is 28.05 times 7, this is a constant, over the span. The effective span is 8 here, and that clearly reduces my allowable L over D. So it gets reduced from 28.05 to only 24.5. So I have my final modified L over D. This is my allowable L over D. Now I have to compare it with my actual L over D. Again, this is just a ratio. It is unitless. And my actual L over D, I have the D here, okay, and I have the span. So it's 8,000 divided by 550. That gives me 14.54. And that since this one is smaller than the final modified allowable L over D, then my deflection is okay. Simple as that. So here I'm back in our design problem, and that since we have the D and we have the area of reinforcement, well, probably we just gonna apply the L over D, the allowable L over D. So first step, simply we find the row for tension reinforcement, and this is always the required, okay, not the provided, and that well, the percentage is 1.5%. We don't need the percentage, we just divide it by 100. That gives me 0.015. Now I just compare this with the reference row, and that is my grade of concrete is 30, so I just put it there and check it. Now this one is smaller than this one, that means I'm gonna use this one here, right? Now the additional thing that you have to do here is just to calculate the rho prime, since I have compression reinforcement, and basically you do the same thing here, except that you just put A sub S prime for the compression reinforcement, and you'll find it to be something like this. Right, the K is just 1 because we are talking about simple beams. Now just plug and check, very easy. Simply substitute, we have everything that we need in this equation, right? And that, if you just check it, it comes out to be 14.27. So this is my allowable L over D, and I have to modify it. The first modification, it is the area of steel provided, and providing more than the required. So I'm getting 1.11. I'm taking this figure and then I multiply it by what I have already calculated here. So that gives me 15.8. Do I have to modify further? My span is just 6 meters. That is less than 7 meters. So this is the only modification that I apply in my beam. Deflection check. Okay, now we have to compare this with my actual span to depth ratio. And well, simply I have 6,000, that's my span, over the depth, which is 450. It comes out to be 13.3. And that simply tells me my deflection is okay. And that's how you do the span to effective depth ratio check for flexure members. Alright, that's it for this part, and well, hopefully we're gonna do the next part, and it's going to be about shear reinforcement design. Till then, thank you very much for watching. I'll see you later.